This is a classic question, but it's fun too. And it's two parts, right? So the first question, and we're going to do this in multiple ways. You know that. The first part says, if I start on one side of the earth and build a tunnel that goes straight through the center of the earth and I fall, would it take longer to fall all the way across the earth to the other side, or would it be faster to orbit around the earth? Well, let's find out. It's actually a solvable problem. You think, oh, this is an unsolvable problem, but it's not. Well, kind of. So let's start off with the orbital motion. So if I have this object orbiting the Earth, then it's moving this way, right? But it's going in a circle. It's going in a circle. Let's say it's orbiting at the radius of the Earth. So it's like a low-flying spacecraft, which isn't a bad approximation. I mean, they're not that far above the surface of the Earth compared to the size of the Earth. And so I have over here the radius of the Earth, which I'm just going to call R. And then I have the gravitational force, I'll just call that F, pointing towards the center. And if that's the only force acting on it, then I can write the following. I can say Fr, the force in the R direction, is going to be equal to the gravitational force, which is the gravitational field, G, mass of the Earth, over the radius of the Earth squared, times the mass of the object. I'll just call that m. And that's going to be equal to the mass times acceleration in the r direction, which is going to be equal to mass times the velocity squared over r, or mass times omega squared times r. So omega is the angular velocity. And since I don't really care about how fast it's going, I want to know how long it takes to go pi radians. Right, omega seems like the better option, so I'm going to use this omega squared. So let's rewrite this one equation and just solve for omega. So I had g, and this is a scalar equation, right? I've already said they're all in the same direction. Mass of the Earth over r squared, mass, is equal to mass omega squared times the radius of the Earth. Mass cancels, divide both sides by r, I get omega squared is equal to g, mass of the Earth, over the radius of the Earth cubed. Now I'll take the square root. Omega is the square root g, mass of the Earth, over r cubed. Now, if I want to find the time, I'm not going to put the numbers here, but I could find the time. So let's say the angular velocity is the change in theta with respect to time. And so if I want to, I could solve for delta t. Delta t is going to be equal to delta theta over omega, which is going to be equal to delta theta. And if I want to do halfway around, half time. It's called half time. Not like a half time in a game, half of the time. Half period. It's half a period, I guess. So I would say delta t is going to be equal, let's call it t 1/2. It's going to be equal to pi, right? If I go halfway around this pi, and then I have to divide by omega. So that's going to be multiplying by the square root of r cubed over g, mass of the Earth. And that would be time 1/2, which I wrote twice for some reason. Orbit. That's the orbit method. That's not too bad, huh? See, we can do that. Now, falling through the center of the Earth. You think, oh, well, we can't do falling through the center of the Earth. We can do falling through the center of the Earth. We do have to have a trick, though. So let's draw the Earth. And then here's my little, there's my tunnel. It's just a one-dimensional tunnel. So we do have to use a particular property. So if I am right here at that point in the Earth, then I can draw a circle, a sphere, like that. And it turns out that the gravitational field only depends on the mass that's closer to the center. So all of this stuff does not contribute to the gravitational field at that point. This is the same thing that happens with Gauss's law. It's a consequence of having a spherically symmetric 1 over r squared gravitational field. So I can write this. The magnitude of the gravitational field is going to be equal to g, and I'm going to call this just lowercase m, not the mass of the Earth, which I just realized I used that twice. But you'll get over it. I think we'll be fine. Divided by this radius, we'll call that r squared. So that's the magnitude of my gravitational field. So now let's imagine that I have an object in this xy plane. I'm going to use the x-axis. So if I have it right there, I can calculate the gravitational field and I can calculate the gravitational force. So the net force on the object is going to be equal to the mass. Oh, I shouldn't have done that. Let's call that MO. That's fine. Times the gravitational field, G, M over R squared. And remember, that M is just this M. Do I have a pen, a colored pen? Well, I don't. That's fine. And that's going to be equal to the mass times of the object times the acceleration. So let's find this mass inside of the thing. Really, let's find a better expression for G. So if I have this is my mass, well, let me start off with the density of the Earth. The density of the Earth is not constant, and we'll get to that in a second. But if the density was constant, then the density of this whole Earth would be the mass of the Earth, ME, divided by the volume of the Earth, which is 4/3 pi radius of the Earth cubed. If I use that, I can find the mass inside. It's just going to be the density of the Earth times the volume of this sphere, which is going to be 4/3 pi little r cubed. So if I put those together, I get mass is the mass of the Earth over 4/3 pi r cubed times 4/3 pi r cubed, and those cancel. And I get the mass of the Earth times r cubed over r cubed. And you notice how I say r, right? I can tell you it's lowercase or uppercase by the way I say r. So if you're just listening to this, you should know that that's r cubed over r cubed, just like I wrote. That's just a little joke. And that's the mass. So I can put that in for this, and I get this equation becomes, well, first of all, those silly MOs cancel. So we're cool with that, right? Cool? Yeah. So I get G times the mass, which is going to be ME r cubed over r cubed divided by r squared, and that's going to be equal to A. And then this cancels somewhat. I get G, mass of the Earth, over r cubed times r. And remember, I'm in the x direction. So let's just write that as r. But if I go back to my x equation, I have now the following. This thing is going to be equal to, the force is in the negative, if this is a positive x, it's going to be in the negative x direction, negative G, mass of the Earth, over r cubed times x. And that's going to be equal to the acceleration, which is the second derivative of x with respect to time. And maybe already you see the great thing about this problem, that this is already solved. We already solved this problem because I have negative, that's a constant, x, second derivative of x with respect to t. But don't worry, I'm going to solve it for you because I care. Okay, so I get negative G, mass of the Earth, what did I say, over r cubed, x is the second derivative of x with respect to time. Now, how do you solve an equation like this? The answer is you guess, right? So first of all, I'm gonna make a substitution. I'm gonna say hint k is equal to no. I'm gonna say k over, well, that's kind of giving it away. Let's just say b. I was going to make it a spring constant, but that's not the spring constant. So b is equal to, this is a constant, neg g me over r cubed. That way I don't have to write it down. So now I have negative b, x is the derivative with respect to time twice of x. Now I want to solve this equation by guessing. So this says I'm going to take the derivative of a function twice and get back the function with a negative constant. And there are several ways to solve that, but I'm going to just pick one that I know will work, and it's the easiest to deal with because I'm not really into solving equations right now. So I'm going to guess. Let's put guess. X is a function of t is going to be some constant a times cosine omega t. So let's take the derivative first of just at once. The derivative of that with respect to time is going to be equal to, the derivative of cosine is negative sine, so I get negative a, and then I have to take the derivative of the inside, so I get an omega term, and then I get sine omega t. Now we can take the derivative again. The second derivative of x with respect to time is going to be equal to negative a. The derivative of sine is cosine omega t, but I have to take the derivative of the inside, so I get another omega, so I get omega squared cosine omega t. And you'll see that that is equal to negative bx if omega squared is equal to b, right? It doesn't matter what a is, right? Because that a is in the x. A, actually, we can find that from the initial conditions. We will in just a second. But it doesn't really matter, to tell you the truth. The a is the initial position. I'm going to go ahead and tell you that. So if I go back over here and I say omega squared is equal to b, which is g mass of the earth over r cubed, and then I take the square root, I get omega is square root of g mass of the earth over r cubed. And that's to oscillate back and forth between the sides of the earth. And oh my goodness, look at this. Let's go back a couple pages. This is amazing. The same thing. So I don't even have to do this if I don't want to. I could solve for that time, and I don't have to, right? Because they have the same omega, they're going to have the same half time. So it takes the same amount of time to fall through the earth as it takes to orbit halfway around the earth. Do you want that number? Well, we'll calculate that number in just a second. Let's go ahead and model this in Python just because it's fun. That's what I want to do. And then I'm thinking, I don't know that the model is going to be that useful. So I don't think I'm going to do that. Instead, what I'm going to do is to look at a different model for the density of the Earth. Sorry, I had to get more paper. So one of the assumptions that we made over here was that the density was constant. And the density of the Earth is not constant. In fact, the density of the Earth changes. Let me show you over here. I have this on the computer. You can find this if you look for it. It's not too hard. Let's see. There. This is the density of the Earth as a function of the radius. So you see in the inner core, it has a density of, about 13,000 kilograms per cubic meter. And then toward, of course, the oceans, 1,000 kilograms per cubic centimeter. But it varies like this pattern. And I don't want to do that exact same pattern, but I could. Instead, let's just pretend that it's a two density Earth, right? So I have a density in the inner core right here, up to about 3,500 kilometers, so 3.5 times 10 to the 6. Anything below that is going to have a density of, somewhere around right here, say 11,000 kilograms per cubic meter. And then on the outside, it'll be around, somewhere around here. Okay. Well, in fact, the outer density, if I do that, I may get a different mass. So I need to recalculate the mass. But let's just show how I would calculate both of the objects. So let me go back to the paper and we'll talk about our plan here. So let's go back to the orbital motion. So if I have orbital motion and I have a double density Earth, just two, right? So row 1, row 2, and I'm over here. Well, it doesn't matter. It doesn't matter what the density is. All that matters is that it's spherically symmetric. So all I care about is the total mass. So if the total mass is the same, the problem is the same. So I still have omega is the square root of, what was it? G mass of the Earth over the radius of the Earth cubed. That's still the same, right? It doesn't matter. Now, what if I'm falling through the Earth? Well, now I'm going to have a different calculation for G, lowercase g. So, again, if I'm in this region, we'll call this region 2. Region 2. I do need to know the mass of this. I'm thinking this is a little bit more complicated than I wanted to, because I'm going to have to find the volume, I can do it. This volume. I'm gonna write it out. I'm gonna do all the calculations in Python though. So this volume right there. So let's say we're at some value in region 2. So R is greater than 3.5 times 10 to the 6 meters. Or X, we can call it X. If that's the case, then I can calculate the mass. It's going to be the mass of the core plus the density 2, right? Density 2, which is in this region over there, times volume 2. So volume 2 is going to have to calculate it as 4/3 pi r cubed, the volume of the whole thing, minus 4/3 pi r, what did I call that, r1? Let's call that r1. So let's say this is r1, and this is r2. This is the radius of the Earth, r1 cubed. So what I'm doing is finding the volume of this piece of a sphere. I'm taking the volume of the whole thing and subtracting out the volume of the core. Okay, and that will give me the density times the density right here plus the mass of the core will give me the total mass. And then I can say the mass of the core is equal to 4/3 pi r1 cubed times rho 1, right? The density of that. Now, once I get to region 1, which is the inner side, then so r less than 3.5 times 10 to the 6. I use the same method I had before. So I can use the exact same expression, which was that's the density. I'm trying to think. Well, I'll just calculate the density as the mass is equal to the mass of the core, which I'm going to have to calculate beforehand, times r cubed over r1 cubed. Now, how do we model the motion? So what we're going to do is to break it into small time steps. I'm going to break it into delta t of 0.1 seconds. Okay. During that time, I can calculate the force. And you don't 100% have to do this, but it just makes it easier. So the force is going to be equal to negative g x times m. I forgot the m. And that's going to be equal to m times a. So I can calculate a. A is going to be equal to negative gx, where x is the x value. Now, if I assume a short enough time interval, I can approximate this acceleration as constant. And I can say this is delta v over delta t, which is v2 minus v1 over delta t. And I can solve this for v2. So v2 is the velocity at the end of the time interval, v1 plus a delta t. Now I can assume v2 is constant, so it's delta x over delta t, which is x2 minus x1 over delta t. So I can solve that for x2, x1 plus v2 delta t. So this is my plan. Calculate the density, calculate the mass, use that to calculate g, right? So g is going to be equal to, g is g m over r squared. And then use that g to find the acceleration, use that acceleration to find the velocity, update the velocity, update the position, and keep on going on. And I want to see how long it takes to go through the whole Earth. And we compare that to the time it takes to go through the whole thing. So we got some work to do in Python here. And I've already kind of started. So I have that graph. I've already picked some values. So let me make this bigger. Sorry about that. Bigger, 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 bigger. That's good. So I have the radius of the Earth, the gravitational constant g. I did the mass of the Earth, but I'm going to recalculate the mass of the Earth. So I have the radius of the inner core, 3.5 times 10 to the 6. Rho 1 is 11,000 kilograms per cubic meter. And then I put rho 2 as 5.9. Is that what I wanted? 5.9. That seems a little high. Let's just go with 5. Now, the first thing I'm going to do is to calculate the mass of the core. So the mass of the core is going to be the density of the core, which is rho 1, times the volume of the core, which is 4/3 times pi times R1 cubed. Now I need to find the total mass. So that's going to be the mass of the core plus the mass of the outside stuff. So let's say V out. Let's just do it all at one thing. So this is going to be mass, no, it's called ME for the mass of the Earth, because I changed that. It's going to be equal to mass of the core plus the volume of the outside, which is going to be 4, let's see, put in parentheses again, 4/3 times pi times the radius of the Earth, which is just r cubed, minus 4/3 times pi times r1 cubed. And all of that times rho 2. And let's print these two. Print MC equals the mass of the core, MC in kilograms, and print ME equals ME kilograms. Let's just see. Okay, so you see here that I have a higher mass than before. So I had, am I on the right thing? Yeah, I am. I had a mass of 5.9 and it went up to 5.1. If I want to fix that, I could do that. Let's just change its density to a little bit lower, 4.5, and see if that works. It doesn't really matter. That's pretty close. 4.3. There's a way to solve this so you could get it. That's really close. Why am I still doing this? Okay, that's close enough. So now I have the correct thing. Now let's calculate T 1/2. I call it T12. T12 is the time it takes to orbit halfway around. And I already said that was equal to, looking at my equation, it was equal to pi times the square root of the radius of the Earth cubed divided by g times me. And let's print that. Print T12 equals T12 seconds. That's how long it takes to go halfway around the Earth. Okay. Now we can compare that to moving through the center of the Earth. So now we need to do that. So let's say t equals 0, dt equals 0.01. Now I put 0.1. We can change that later if we want to. Do I need the mass? No, I don't need the mass of the object. I don't need to do that. We're big enough for that. I do need my initial x is going to be equal to the radius of the Earth. My initial x velocity, I'll just call it v, is 0. I'm starting from rest. And I think that's it. So let's go ahead and say while x, I want to let it go all the way through the center of the Earth and stop. And I'm afraid that it might not make it to the other side. So let's say while x is greater than 0. Let's just do while, I'm trying to think here. Let's just say while t is less than, what did I just run this at? 2,500. Let's just see. Let's just see what happens. Do I want to graph this? Yes, I do. Let's make a graph. G1 equals graph. Title equals fall through Earth. X title equals time. Y title equals X. And then I like to put this. Width equals 400. Height equals 200, or it doesn't, it's just too big for the graph. And then F1 equals G curve. Color equals color.blue. Okay, so now the first thing I'm going to do, I'm looking at my little equation right here, is to calculate the G. So, and to calculate G, I need M. So, let's say this. If X is greater than R1, I'm in the outer part, then do the following. G, let's say M equals M core, which I've already calculated, plus I just need my little equation right there, which I put. It's 4/3 pi r x cubed. So 4/3 times pi times x cubed, which is r, minus 4/3 times pi times r1 cubed. And then that's my volume. I need to multiply that by rho 2. Okay, so that's my total mass. Now I can use that to calculate my gravitational field. So G equals G times m over x squared. And that's my acceleration too. So A is actually going to be equal to negative G because it's in the negative x. Ooh, that G is going to always be positive. So times, I should have done this as a vector. So that's the magnitude of my acceleration. So let's just do this. If x greater than 0, then GA equals negative G, else A equals G. I know that's dumb, but who cares, right? It doesn't matter. Okay, so now I have A. I can update my velocity. V equals V plus A times dt. I can update my position. X equals X plus V times dt. I can update time. T equals T plus dt. Now, if it's inside, I'll say else. If it's less than R1, then I'm going to be else. So now M equals just the density, which is the rho 1 times the volume, which is going to be 4/3 times, I've already calculated rho 1, 4/3 times pi times x cubed. G equals G times m divided by x squared. And again, I'll have to say if x greater than 0, actually this stuff is the same. I'm just going to copy that. I really don't know if this is going to work. Oh, that's not going to work. There. Okay. And then this is the same too. And that goes over here. Okay. So that should do it. Now let's go ahead and plot too. F1.plot tx. Let's just see what happens. This might be a disaster. I feel a disaster coming on. Fall through Earth 2. Save. I feel like I made a mistake. I feel a mistake. I feel a mistake. Could be right. Run it. Aha. There are not enough attributes to string different rotate. What the heck? T equals 0, x equals r. Let's just do this. I'm going to print down here, print x and t. Let's just see if it prints stuff out. No. So it's higher than that. So let's say print t. Didn't do that. Oh, you know what? I bet it's a graph problem. Let's get rid of that. Let's get rid of that. Graph G1 graph title, X title. Aha, equals. No, equals, that's right. Title, X title, Y title. Let's just comment out these two things and see if that, I feel like that's a problem. No. X to string add divide. Did I? G. Let's put print right here. Print R1. Didn't get there. Print R. Didn't get there. Okay, let's get rid of this. What the heck? We'll get rid of that. Okay. Let's get rid of the plot. And let's just see if it runs. Okay, it's running. So it's a plotting problem. So let's put this back in. Put this in. And run it. And that's the problem. Okay. So if I put just F1 in. F1 equals G curve. Aha! Oh my gosh! Color equals color dot blue. I'm so dumb. Okay, but I didn't plot it. I told you I felt it. I felt that there was something wrong. And I was right. There you go. Okay, so this is kind of cool, right? It starts up here at an x value, and it ends up here at a negative x value on the other side. And you'll see that it did not get to, oh, x is negative over here is when it hit the other side. Wait. There's my x value. It blew up. So see, there's 6.62, and it doesn't come back. Okay, so there's something wrong with my calculations. It's blowing up. So it's somewhere over here. If x is greater than 0, the acceleration is negative g. Otherwise, it's g. So if x is greater than 0, that's right. And over here, x is greater than 0. A is g. Okay, I've already spent 31 minutes on this. I think this works in principle. I'm going to fix it. Sorry for wasting your time. I'm still going to post this video because I like the first part. I should just cut off the second part, but I'm not going to do that. I'll fix this code.